I'm Cass. I just wanted to introduce myself before we got into the final year video. My topic was trying to figure out the goal of human movement through machine learning. So I've done that through a variety of k-nearest node algorithms that I've done. I spent the last year on it. It works for most cases, but we'll get into that shortly.
So just a quick overview on how KNN works. KNN stands for k nearest nodes. So in here, in this situation, a node is a data point, much like this data point there. And so it's really simple, there's only 4 steps to it. So the first step is to isolate the current point you're trying to predict. That is Mr. Blue Guy over here. Next is we have a look at our training set, and we'll add that to the mix. So here we've got our 2D data. So that's all plotted, and we've got all 5 goals. They're all multicolored. And here is our point we're trying to mask here. So then we do our distance metric, and we will find the top k values over there. And what we do then is find the most common, and right now that is goal number 2. So we'll say at this time, when you're moving in that direction with all these other nodes, you're going to be going in the same direction heading to goal 2 as well. Here is basically the main setup for the code that I was running. So here is my main for my one-dimensional, where we just write in the data and all the file names, set up what we wanted to test, and then for the number of files we had, what we wanted to do is test them all, and then print out how well they went. So on our actual KNN algorithm, you'll see it's not a very long code, it's really short, because KNN is one of the simplest algorithms you can get. So all we need is a k value, our training data set, our test set. And so what we do is for every time step, what we do is we get the time at t equals 1, and then we subtract that time from every entry in the training data set, and then we find the Euclidean distances between, all the theta values and all the velocity values. What we do is we then sort that list from shortest to longest, and then we keep the top k values. So those are going to be our k closest nodes. Then we find the mode of it, and that one is then our goal for the time. So our 2-dimensional one is very much the same. Load in the data, run the algorithm. Here we're using a cosine KNN. So that's essentially the same, except for this line here. We're turning the x and the y velocities into an angle for the direction they're moving in. And there's just an extra line here to get it in the right format, but you find the Euclidean distances between the x and y distance, and then to get the distance between your angles. And then what we did now is I just added them together, and I weighted the angle to be 18 less, because the values are bigger, and then the same thing, sorted them shortest to longest, got the top k values, got the mode. For our 3D data, same setup, so we got a cosine weighted this time. Cosine weighted makes it a little more complicated. So for every k value, what we're doing is we get the top k values. For each top k values, we'll have a distance, and then we'll have the goal associated with it. So what we do is we inverse all the distances. So then your smaller distances have bigger values, so they have more weight. And if that weight is for that goal, we add it to the tally. And then overall, we get the maximum tally, or the one who had the most numbers, and then that'll be our current goal. Okay, let's start going through some of the results I had now. So here are the results from my one-dimensional data. I'm going through the report I wrote up because everything's just there and it all looks nice and neat. So basically, with we had a set of k values that we choose to put in to the function. So I generally started with 30, 50, and 100, just to kind of get a broad range to see what worked best. Generally, when you get told about k-nans, you get told to pick a low number, less than 15. But because of the number of points we had, 15 wasn't enough, and you'd get way too many goal changes. So you had to choose one of the larger numbers. So here we ran them all. All of them we had a success rate above 90. That's first off the bat, which is great. So the one-dimensional data works really well. So we just picked the best one out of here, which we picked 100 because they had the least extra goals or extra goal changes we weren't supposed to have. And after that, I chose a bunch of k values closer to the 100. And 110 got the best amount. Again, just because there was less accurate. But a success rate of 98.57 is amazing. And if we look at the graphs that we had, here, users moved in the blue, the actual goal is the yellow, and one predicted is the orange. So it maps the blue quite well. There is a delay here, so one thing you note with the data set that we have is the actual goal moves up and then down, and then the user later on has then gone up and then down. So there's some issue with the timing on how it's all been recorded, because it's like telling somebody, stand up, sit down, and then 30 seconds later they'll stand up and sit down, even though you told them to sit down was the last instruction you gave them. But besides that, you still had a less than a 0.5 second turnaround for the machine learning. The other ones went just as well, followed it all through. Well, this one had a bunch of extra goals, but they were one of the few cases where that happened. If we skip ahead to the two-dimensional results, the two-dimensional one was the first one that didn't work with the Euclidean distance. So that's where we had to actually start changing our algorithm, because we didn't get 90% off the bat. We had 13% that was too much, or 11. So after this, we changed the cosine, which meant you're comparing x, y, and theta, as opposed to x, y, x velocity and y velocity. We just had this theta instead. So if one guy was moving in that direction, I wanted the person moving in this direction to be considered similar. Because I feel like heading in the same direction was more important than whether they were there or whether they were there. So the results here went well as well. We actually got a threshold 10.81, which is just above the one we wanted. We need to get something about 10. One thing you do notice as well is that for a few of these cases, we actually missed goals. So we were told to go to 1, and our algorithm didn't, it went straight to 2. But messing around with that k value again, we got it down below 9 by choosing a k value of 60. We still have these missed goals. So there are cases like the one here, where goal 1 we didn't actually go to. So goal 1's down there. Our algorithm went straight to 2, and then up to 3. It never went down to this one level, which was disappointing. But when you look at the user, just moved in one direction, so not really much we can do to explain that. But as far as that, the rest of them worked pretty well. This one had a little bit of a large delay, but followed it pretty closely. And considering when the user started moving, it's pretty close. It's, again, with the time delay, I think that's there in the data issue. So then we want to redo it. I'd like to recollect the data or do it again myself so I can make sure everything lines up, because, they're saying go to 5, and then go back down to 3, and then you're like, okay. But while they're telling them to go to 3, you still go to 5 and then come back down. Well, let's go to 3 yard, and the 3D results is where nothing went well. Euclidean didn't work, 33. The cosine didn't work, 33. We tried a weighted cosine, 24.4. And that's where your points close by are worth more than the points further away. So this is worth 4 points, and this is worth 1 point. Just because of how close it is. What we did here is we did an inverse relationship, so this is x, and this is 3x, then that point was with 1 on x, and that point was 1 on 3x. So it was just worthless. That's how we put it all through, but none of them worked. And we tried so many things. I tried changing the k values. I tried changing the parameters. I actually got to the point where we had our point here. If we had any points outside this circle, they were taken out of the list. And I also added in if they weren't facing, if this person was facing there, if they weren't in this semicircle, they were taken out as well. So I hoped if we could eliminate all the ones that are close by, but pointing in the opposite direction, we'd get better results. But it improved it slightly, but was still sitting at the, 24. Then we changed a few things. Yeah. Again, that was the circle. So the circle, we had a thing of 30 that we're taking out all the points of. And then we're sorting the distances purely based on the angle between the two.
and we managed to get it down to 20.69. It's still 10% off. We still got another 10 to go, but it was the best I was able to get with K&N. So I think either we go through and we collect the data, or we consider looking at a neural network. That's something I'd like to start doing. But if you look at the results for the 3D to see what's going on, it's all over the place. I've got true goals over here that don't make any sense. I've got 4 peaks over here, they go up and back down. Like 11 extra goal changes. It's not viable, and by the looks of it, it's for a fair amount of time. So it's not even that it autocorrects for itself like the other dimensions do. It kind of staggers. In here, it does it as well, goes up and down, and then back up and down again. So, and this one also missed a goal. Never hit number 4 up here. So the 3-dimensional data didn't go too well. But like I said, I'll get you some videos as well. So let's look at some of the videos I made. Let's choose lucky number 7. So this is the 1-dimensional data. So we have here the current position, the predicted goal, and the actual goal. So you can see the machine learning goal tends to swap. It goes down pretty much instantaneous after the blue one moves. So you can't really see a difference there, which is indicative of the last results we saw where they fared really well and there was no delay with that. Let's go down to a 2-dimensional data. These take a little bit longer, but their results were well as well. There we are, pointing down there in the bottom right. Goal changes down the bottom left. User starts moving. Goal changes as well when he's about halfway there. Alright, so that's not a bad one. If we look at another 2D one, starting out there in the bottom left, goals changes to that one. He's followed. That's changed pretty much instantaneously. So I'm really happy with the way that's turned out. 3-dimensional ones, data, that's where they didn't go so well. Okay, so let's look at the 3D one. Let's pick that number. Alright, we're moving towards that goal. It's taking a while. The machine learning goal they did a loop before they came down to the one it was supposed to be, which isn't what it's supposed to do at all. It's just heading to 1. So on the 2D graph, that's going to look really nice because it goes from 1 to 2 to 3 to 4. But, you know, when you picture it visually this way, it makes no sense that he's passing through all 4 goals to get to the end one. Alright, let's look at another one. Let's go 66. Alright, goals at the top left. He starts moving. Goal goes top left. That's good. But then once we get there, it's going down to the bottom. Don't know why. It might be because we're taking out the list distance. We're basing purely off the direction that they're moving in. So because he's already there and he's moving on these small distances, but in the angles, if he moves slightly down, it's going to take out all the ones that just hover around there and say that he's going down to the bottom goal, which I think is what's happened. But we knew the 3-dimensional data wasn't going so well. So the next thing I would like to do to improve it is I'd really like to try a neural network to try and think things moving. Because one thing you will know about the K&N thing is at time equals 0, the K&N algorithm will pick a goal, it'll output it, and then it'll forget it. And then for t equals 1, it'll do the same thing. It'll try and figure out the goal from everything at that time and forget everything about the things before it as soon as it's figured it out. Which I think is a waste because obviously if you're sitting at goal 1, the chances of your next goal of being goal 1 are more likely than you going down to goal 4. So I think there's a bunch of overlap which could be utilized, and I think a neural network would be an easy way to do that. So we could have goal 1, 2, 3, 4, and then we'd have our previous goal. I guess you'd try it with 1, and then maybe you'd go to 2 or to 3 and see if having more goals will make a difference. Then we just have our inputs, and our x, y, z, and maybe theta. But this is something I'd like to try. Unfortunately, with my project description, I restricted myself to K&Ns only. So this is, I guess, something that I'd like to do afterwards that I probably will do. So, thank you for that. Thank you. That is my project work. If you have any questions, feel free to ask me. Thank you.